Hi, my name is Kayla. I'm presenting this work that was mostly done by Akshar, who's not able to be here, and that we also worked on with Seth Cooper. So our motivation for this work is that we can use procedural content generation to generate static levels, but it's hard to ensure that those levels are solvable. And the way that we approach this is by generating levels and their solutions at the same time by formulating this as a space-time problem. This builds on work that I presented last year called Space-Time Wave Function Collapse. And very briefly, the idea is that we take all the time steps in a level solution or frames in the level solution, and we stack them together to make a three-dimensional space-time prism that's passed into an off-the-shelf 3D wave function collapse solver. And we were able to kind of use this as a proof of concept to show that we could generate solvable levels this way. But we ran into a few pretty significant limitations. The biggest one is that it was really, really slow to generate levels, including really small levels, making this not feasible to use for any kind of real-world application beyond this proof of concept. In addition, we found that it was sometimes prone to violating global constraints, such as by generating multiple players in a level. So what we decided to do is we decided to port this kind of space-time idea into Seth Cooper's project Sturgeon, which, like wave function collapse, learns input patterns from examples, but it formulates level generation as a generalized constraint-based problem, which can be solved using a SAT solver, which we hoped would make this a lot more efficient. In addition, because it's using kind of a more generalized constraint-solving problem, we can introduce additional configurations and global constraints to hopefully avoid violations. Now, Sturgeon is a two-dimensional level generation program, and we formulated this problem in 3 dimensions. But it would be a huge undertaking to make Sturgeon support 3 dimensions, so instead, we reformulated our problem to use this 2-dimensional film strip representation, where all the frames in the level solution are separated by these specialized void tiles to turn our 3D problem into a 2D problem. And we tested this with a couple different methods of learning patterns and generating levels. So the first method was designed to be as similar to space-time wave function collapse as possible. So it's learning all of these patterns, which are just the pattern in one frame separated by the pattern in the next frame by an amount of space that is equal to the height of the level. And you can see that at the bottom here in the final frame, we use these terminal tiles to represent the end of the level. And this is designed to ensure that the level reaches a state that would be considered solved in the input levels, which is the same method that we used in space-time wave function collapse. And this is what this looks like in the Sturgeon configuration for the level generation. We use Sturgeon's configuration grids. So the tag grid here on the left represents the shape of the generated level. And then the match grid represents tiles that we desire to be in the generated level. So here, it's kind of hard to see, but there are these spaces that are on either side of each frame in the level that's representing padding. And then in the bottom, the final time step, again, is these terminal tiles so that our generated level will reach a solved state. The other method that we tested for this is called the diff method. Now, this uses patterns that are based on changes between time steps. Instead of just taking entire patterns from each frame, it only looks at the part of the pattern that actually changed. And we also take advantage of Sturgeon's pool grid so that we can learn patterns that are specific to the first time step in the level and patterns that are specific to the last time step in the level, which removes the need for those terminal tiles because now we're only learning those patterns separately. And it also allows us to have constraints for the start state of a level. And then in between, what we find interesting is that we're kind of representing patterns that represent how the level can change over time. So these are input-output patterns, which so here for player means that whenever a player tile is found, it checks the current frame and the next frame, and also the current frame and the previous frame for valid states. So here, if it finds a player, it knows that the player has to be next to a space on the right or next to a door on the right. If it's next to a space, then the next frame, that's replaced by a space and then a player. If it's next to a door, the next frame can be replaced by a space and a goal. Whereas for the previous state, there's only one valid state, which is that the player has to have a space on the left and be preceded by a state where it was a player with a space on the right. And you can also tell from these patterns that there's no way for the player to not move between time steps. All of these patterns show that the player is moving in between time steps, whereas for something like the door or the space, they have a pattern where it's just the space replaced by a space in either the next or the previous time step, and similarly for the door. And that also demonstrates how the diff method is only learning the parts of the level that changed. So it's not looking at what's next to the door or the space in that case where the door or the space doesn't change. And this is what that looks like in the sturgeon generation configuration. It's basically the same, but without those terminal tiles. And we're now using the pool grid as well as the tag and the match grids. And you may have noticed that this method kind of requires that all of the patterns need to be the same height, which means that the levels would have to be the same height. But it turns out this is pretty easy to get around. We can just remap patterns from input levels that might be of different heights into one desired height for creating the patterns. And if we want to generate an output level that has a different height, we can also just simply remap the discovered patterns to that height. So that's pretty straightforward. So to test how well this works, we did a comparison to the original 3 games that we introduced in the Spacetime Wave Function Collapse paper, which is Field, Maze, and Small Sokoban. And this is what Field looks like for the configuration for the block and the diff method. And we found, very excitingly, that the sturgeon-based methods are over an order of magnitude faster than the original methods. So we can see for Sokoban, even this tiny level took an average of 80 seconds to generate from space-time wave function collapse, and both of the new methods take under a second, especially diff. And we also, because we're using Sturgeon, which uses a SAT solver, we have a 100% success rate in solving, and because we're using a global constraint that there only be one player object, we never generate an extra player. We also found that space-time wave function collapse and block, which have very similar methods of generating their input patterns, also have a very similar effective length of the level, which is the number of time steps it takes for the level to reach a solution, whereas the block method improves on that. So because we had these huge gains in efficiency, we were able to create an interactive editor where a designer can edit any time frame of the level and get generated a level that matches their constraints. And we were also able to test this using larger games such as Block Dude and a larger version of Sokoban. And we found that even with these larger levels, we were still getting times that were acceptable for this kind of real-time generation process. So even the largest version of Sokoban that we tested took an average of around 10 seconds to generate, which is not lightning fast, but is a lot better than what it would have taken in space-time wave function collapse, which would probably be hours. And now we have a little recorded demo of our interactive editor. You can see that the designer can place whatever tiles they want in any frame in the level, and the generator will adapt the level to match their specifications. And this is sped up about twice as fast as it would be. So we can see how this is changing as the designer makes changes to the level. And then it's going to get to a point where the stat solver can no longer solve it. And then it goes away. But that's pretty easy to correct for. You can just delete the last constraint that you added to get it back to a state where it is solvable. And we did the same thing with Sokoban, which I'll just show a couple seconds of, just so you can see. So we came up with a couple of use cases for this interactive editor. The first one is having a constrained path. So this designer can specify a path that they want a solution to the level to go through. Of course, this is not that the level has to go through this solution. It's just that this solution exists in the level. So you can see that all these generated levels have the same solution path that they're going through, but they are different. And we did the same thing for BlockDude again. We also thought of the idea that a designer might specify an interesting intermediate state that they want a solution to pass through. So here, they wanted to go through this set of blocks in one of the solutions to the level. And that could be useful if there's some like cool shape that you want to show at some point in the solution, but you don't necessarily want to put it in the beginning of the level. And similarly, we have this for BlockDude. So some of our future work ideas for this is that we'd like to apply other two-dimensional PCGML techniques to this 2D film strip representation so that we can use the space-time representation on these 2D techniques. And also we would like to automatically find pattern shapes and context to better capture game mechanics, because currently we are just selecting what we think is a good pattern size for these games. And finally, we're looking into merging patterns from top-down and side view two-dimensional games to create new games in a three-dimensional space. So for example, you could take Sokoban, which is a top-down block pushing game, and BlockDude, which is a side view block lifting and jumping game, and merge them together to create a game where you can both push blocks and pick them up. And that's all. Thank you. Yeah. Yes. Yeah, so I should have kept sharing, but so the patterns are kind of the salient tiles in the pattern separated by a bunch of null tiles, which are kind of the height of the input level. And we can just change the number of null tiles in between kind of the salient parts of the pattern. Yes. Well, we found it really fun to look at the games with the film strip. And yeah, I guess theoretically there could be other ways of representing that. You could let people kind of, I guess, page through time steps if they want to use this time step base. You could just let people edit the starting frame of a level if they just cared about kind of what the level looks at the beginning and they want to know that it's solvable. But we thought that the film strip was fun to work with, so that's why we kept it. Yeah. Solutions that are fair that shorter than the longest of that. So maybe compare the theoretical path solution to the No, we did not. We did find that for one of our games, Maze, space-time wave function collapse often generated multi-step solutions, but the two new methods always solved the level in just one time step. And that's because in Maze, it's like a more highly kind of constrained space. It's very dense. They're very dense levels because they're filled with walls. And so the new methods kind of devolved to just putting the player directly next to a door. Whereas in space-time wave function collapse, the reason it doesn't do that is because we initialized the level to randomly place a player in a door. So it was forced to take multiple time steps. So we did run into cases where this is kind of likely to generate shorter levels just because it's using kind of this constraint satisfaction method. And it's not, we don't tell it to generate like longer levels. We just get the longer levels if we're lucky.
Building on that last question,
Yeah.
specify the player who can return.
Yeah.
Have you ever ended up in situations where they just like move back and forth between say two squares forever and like or like you can, that's a constraint that you can technically respect while spiritually just ignoring.
Yeah, and we did definitely see that in space-time wave function collapse. I would have to ask Aksha if you ran into that specifically with this. It wouldn't surprise me. Anyone else? No? Okay, thank you.